Okay, so I'm going to explain all the elements of the system and the experiment, but let's start with the simplest component, which is the ABC triangle, which is inscribed in this brown circle and circumscribes this inner caustic, okay, centered on I, the outer circle centered on O, and you have here, ignore the motion of all the other objects, just focus on ABC. You have a standard traditional Chapple n equals 3 Poncelet family circumscribed about interscribed between two circles, okay, so-called bicentric family n equals 3, okay, or the Chapple Porism, ABC. Nothing new here, okay. Now what I'm going to be doing first of all is I've created a circle here, this dotted brown circle, on which I can slide my caustic. I can slide the caustic. You just focus now on that inner brown circle, the caustic of the Chapple Porism. And of course, if I do this, I preserve Chapple's Porism, right? Because I'm basically rotating the caustic rigidly. So you can see here that ABC, the dotted blue triangle, continues to be in a porism. So I can place my caustic anywhere here. I'm doing a rigid rotation of my caustic with respect to the center of the system. And then at any position I place the center of the caustic, I continue to have the Chapple porism because the two circles have already been placed using Euler's formula, and the distance between their centers and the relation between the radii has been chosen correctly. Okay, now what is this experiment all about? I'm going to go ahead and take ABC and apply a projectivity, a 2 by 2 matrix. I'm going to multiply the vertices of A, B, the three vertices A, B, and C. I'm going to pre-multiply them by a 2 by 2 matrix. The coefficients are here, SXX, SXY, SYX, SYY. And they're going to get transformed. They're going to get projected, okay, onto a new triangle, A prime, B prime, C prime. So that as I rotate my Chapple family, I get a projected A prime, B prime, C prime family, which will be circumscribed, sorry, let me say this correctly. It's going to be inscribed, for example, if I put, let's go ahead and do this. I'm going to put a trace here. You can see here that vertex A will describe a conic, an ellipse in this case, which is basically the image of the circumcircle under this projection, okay, under this 2 by 2 projectivity, okay. And likewise, the vertex, the envelope of the sides of this projected triangle are gonna envelop. They're gonna envelop the projective image of that circular caustic, okay? So I've created a new Poncelet family, let me say this very simply, which is a projective image of my original ABC under a certain projectivity defined by 4 numbers, okay? And they're here. So imagine these are 4 elements of a particular matrix, and I'm just projecting ABC, okay? So let me go ahead and turn off the trace function. We don't look at this anymore. But all I want you guys to understand for now is that I simply have a projective image of my Chapple porism here. Okay, if I change one of the coefficients, for example, let's make all the coefficients be equal to 1. Sorry, the diagonal ones be equal to 1, and the off-diagonal ones be equal to 0. So I have an identity transform. So if I have an identity transform, A prime, B prime, C prime is ABC. But I can start stretching along X like that. I can stretch along Y, okay? And I can add these off-diagonal values. They can be negative, okay? Doesn't matter. All it matters is that A prime, B prime, C prime is now a projective image of ABC. And I'm going to be studying the locus of triangle centers of A prime, B prime, C prime. So right here, this ellipse, we've shown in a previous paper, and I'm going to put a link in the description, that for certain triangle centers, for any Poncelet configuration, any Poncelet family, their locus is guaranteed to be a conic. Okay, so I think that the property is that if a particular center is a fixed convex combination between x2 and x3, the locus is necessarily a conic. So if I look at x2, x2 is going to be a conic. Now, what this experiment is about is I want to investigate the properties of this locus, okay? And this locus is swept over a particular cycle of the Poncelet family, right? So this is the locus of x2 for the projected family A prime, B prime, C prime. So it's the x2 of this blue, a solid blue triangle over the base Poncelet family, okay? Now, as we saw before, sweeping A prime and then sweeping and looking at the envelope of one of the segments, okay, this is a Poncelet family. A prime, B prime, C prime is a Poncelet family, some generic one. So the locus of x2 is guaranteed to be a conic. Now let's look at what happens to this locus, okay? As I actually do that operation, which is to move the caustic around rigidly about O, okay? What's happening to this locus? You can see here that the area of the locus is invariant and the eccentricity is invariant. Okay, so this locus is actually moving rigidly. It's an ellipse moving rigidly over the plane here as a caustic of the base bicentric system is rotated about O. Okay, what happens to x3? Well, before I go into x3, let's go into x1. x1, the locus of x1 is not a conic, okay? So I'm going to jump straight into x3, which is guaranteed to be a conic. Now here's x3. If I move, it's also an ellipse, okay? Here's the instantaneous x3. If I move my base Poncelet family, x3 is sweeping this conic, right? Now, if I now jog the caustic, the locus of x3 is a family of ellipses. You can see here that they are no longer rigidly related, right? But what I can look here is on the left, I'm plotting the area of the ellipse, which is proportional to the product of the semi-axis, and the eccentricity, which is proportional to the ratio. Not proportional, but it's related to the ratio of the semi-axis. So as I move I around, you can see here that the area of this family of loci is preserved. Look at how A doesn't change. However, the eccentricity is variable. If I take x4, I get the opposite phenomenon. Now I have a family of ellipses of fixed eccentricity and variable area. Okay? Now this is somewhat intriguing because we're applying a fixed projectivity to ABC, obtaining a new family of triangles, and we're showing that the area of the family of x4 loci is variable, but its eccentricity is constant. And for x3, the area of these variable aspect ratio ellipses is preserved. Okay, now let's do one more experiment. Just before I do this experiment, for x2, you just have a rigid motion of the locus. Okay, now let's do one more experiment. I'm going to go to x3, and I want to now see the locus of the center of this elliptical locus over OI. So I'm going to use the locus function. In GeoGebra, I'm going to say this point with respect to motions of I. So the locus is an interesting curve, and it does look like it's an ellipse, right? The locus of the center is an ellipse. It seems to be an ellipse centered on O, okay? Let's check out where the foci of this ellipse are. So I'm going to put the ellipse tool here. So I'm going to go 1, 2, 3, 4, 5, and I want to see the focus of C1. Yeah, so the foci of the C1 are not necessarily in any specific location. Okay, let's go ahead and forget about that. Let's get rid of these 5 reference points here. But the locus of the center of this family of elliptic loci is an ellipse. Let's color this ellipse here yellow. Yes. Now I want this guy here to be colored. I'm hoping that this is correct, right? Because I seem to be in a, yeah. Yeah, that could be incorrect. Let's here. Delete. Let's do the locus again. Locus, center of the locus over I. Yeah, so you get that. Now, if I go here and I make this be gold, like so. Okay, now what happens to this locus if I'm talking about x4? x4 is also an ellipse. Okay, the locus of the center of the loci seems to be an ellipse, also centered on O. Okay, it's a bigger one, spanning out there. So now you have this other result, right? You get ellipses for both the centers of the loci over positions of I, right? So if I move this I around, you can see that the center of the locus is sweeping the gold ellipse, okay? And that ellipse seems to be also centered on O. Okay, let's see. Now let's do one more exploration. Let's see what's the locus of the foci of this set of ellipses. So let's turn on the locus tool, and this is probably going to be more complicated. So here's one focus over I. Yeah, so it seems to be more complicated. You know, it's not managing to do the whole thing here. Let's do the second one here to see if it completes it. Yeah, it does complete it. So you can see here that it's a self-intersected curve. Let's look at what happens when we go to x3. It's computing. Hope it is. Trying to go back to x3. But it could be that it's gotten into one of those. Yeah, there it is. So, yeah, so this is x5. That's not what I want. I want x3. So I want to see this locus on x3. Yeah, so that's interesting as well. I have an ellipse here for the center. Okay, for x3. So let's look at it. Let's look at how that ellipse is swept. And then for the loci, I have this sort of cross-shaped or sword-shaped curve, which is also quite interesting for the foci, right? How about for x2? So let's have it recompute x2. Should be more elementary, hopefully. Whoops, I take that back, but this is probably just a mistake here. Yeah, let's do this. I'm gonna move I, and I'm gonna redo these guys. I don't believe this is correct. Yeah, so you see it's a simpler object. You can see here that yeah, the center of, and now the loci, the family of loci is rigid, right? The center is moving along that gold curve, and let's go ahead and color these two here as green. You know, let's sweep A. Let's sweep A. Yeah, it's a little unstable for some reason, but as we sweep A, right? All you're doing when you sweep A is you're moving x2 on its own locus, okay? When you sweep I, you're basically now moving the center and the foci. The center is moving on the gold curve and the foci on that self-intersected curve, okay? Which is not elliptic. It's not an ellipse, okay? So I hope this makes sense. Let's go ahead and get rid of the loci here because they are slowing it down. Let's go ahead and recap the results. Hopefully I can do this. Yes. So the family of loci of a projected derivative of a family of bicentric triangles, okay, is, for the case of x2, is a family of rigidly, it's a family of rigidly related ellipses that seem to preserve orientation, okay? So if you look at the axes, okay, over the family, all these ellipses seem to be oriented, so the direction of the two axes seems to be also invariant. For x3, all of a sudden the simulation has gotten quite slow. Perhaps I should save it and reload it. Save. Let's reload. Yes. So for the case of x3, you got this beautiful family of ellipses, which preserves area. Does not preserve direction. You can see here that it does not preserve direction of the axes, as was the case with x2. And then with x4, you got a family of ellipses that preserves the conserves the eccentricity. Seems to conserve also the direction of the axes. Can you tell that they're remaining oriented? If I change the parameters of my projectivity, the orientation of the axis also changes, okay? But once you pick the projectivity, right, like that, you pick that projectivity, then over the family, I am just eyeballing this thing and sort of guessing that the axes are basically oriented in a constant way. Not the case for x3. Not the case for x3. Here you conserve area. And for x2, since everything is rigid, you also don't have any rotation. So this is not even a family of rigidly related ellipses, family of translation related ellipses, right? They're all translations. Okay. All right. So that's all I have. Thank you very much.